Hello everyone, welcome to Linear Model with me, Sarini Abdullah. So in this video, we will focus on multicollinearity problem. So we will learn what is meant by the multicollinearity and what is the consequence if there is a multicollinearity in our model, and then how to detect the multicollinearity, and later on we will see how to solve the multicollinearity problem in our regression model. So let's us have the multiple linear regression model given by this equation beta naught plus beta 1 x1 all the way to beta p xp. So what we want in the linear regression model is that all the x's should be highly correlated with the response variable, because we want them to be a good explanatory for the response variable. However, we don't want it if between the x's here there is a strong correlation. That would be not good for our model. In case that thing happens that there is a strong correlation among the variables, among the predictor variables in the model, then we say that the multicollinearity problem exists. So now we know that what multicollinearity is, then what is the consequence of having a multicollinearity in our model? Let's see this explanation. So this model, we can rewrite this model in the form of matrix multiplication. That is y equals x beta, where y is the matrix of response variable, x is the matrix of predictor variables, and beta is the matrix consisting beta naught, beta 1, all the way to beta p. They are the regression coefficients. So then, in order to use this model, of course, we want to know what is the value of beta, right? So then we want to estimate what is beta naught, what is beta 1, all the way to what is beta p. So we need to do estimation for our beta. And then to do that, we can just have, that in this estimation process, we want to be able to write beta equals something, something. So then we use our matrix knowledge for that. We multiply both sides by the transpose of the predictor matrix. So we have x transpose y equals x transpose multiplied by this thing that is x transpose beta. And then, because again, we want to be able to write beta equals something, something. So then we just group this x transpose x. And then to leave out only beta, we need to multiply this by its inverse. So that's why we have this one, this equation. We multiply both sides of the equation with x transpose x inverse. And then this one will give us the identity matrix. So then we are able to write beta equals x transpose x inverse multiplied by the x transpose y. Now, from this equation, let's see what happens in the estimated value of beta when we have a multicollinearity in our model. So just to make it simple, let's say that we have that x should be like, for example, okay, this is the data. Actually, the x matrix consists of the first column should be a factor of 1 that is associated with beta naught. The second column is for x1 for the first person, all the way x1 to the nth for the nth person, and so on. Here we have the pth column is that the p plus 1 column is the pth explanatory variable. But just to make it simple, let's just have the matrix X like this to illustrate that there is one column there, and the other column is a multiplication of that column. In the reality, it doesn't, this thing rarely happens. That this is a perfect multiplication of one column to the other column, but in the reality, it might be just, this column just kind of like okay, approximately a certain constant times the value of the other column. Probably this is 1.8, this is 2.9, something like that. It doesn't have to be a perfect relationship like this. But this scenario is just put for us to easy to understand later on the problem that exists when there is a multicollinearity in our model. So then, because we want to calculate the beta in here, we want to calculate the beta. So we do this procedure, we calculate the X transpose, and then we multiply the matrix X with the transpose of it. And then from the matrix multiplication, we can get the result is like this. Now look at the result here. So we have here column 1, here is C1 squared plus blah, 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 like this. And we can see that the second column is that 2 times the value of the first column. It means that here in the X transpose X matrix, there is one column that is a multiplication of the other column. Statistically speaking, we say that this column, the second column, is highly correlated with the first column. In this case, it's perfectly correlated. And also, if we examine the row here, we also can say that here the second row is like 2 times of the first row. So we can have that also the rows are strongly correlated, the values within the rows. Now let's see. To be able to estimate the beta, so we have that, okay, X transpose X inverse, how we are going to calculate the inverse of the X transpose X is that 1 over the determinant of this matrix multiplied by the adjoint of that matrix, right? So then in the calculating the determinant, we have to calculate, okay, the determinant of X transpose X, here we have it like this. And then we know that when calculating the determinant, if there is a column that is linear, linear multiplicative with the other column, then the determinant will be close to 0. Okay, so then let's say we have a small change in the value of the X. Okay, we have a small change in the value of the X, then there will be a small change in the value of the determinant of X transpose X. And then small changes in determinant will result in huge change of the betas. Why is it like that? Let's look at the example. Let's say the determinant of X transpose X is 0.001. So then we will have that the beta given by this formula is that 1 over the determinant, blah, blah, blah. And then the determinant here, we put here the value 0.001. And then let's say this is just, okay, some a constant that we get from the calculation. So then before by substituting this value into here, so we have that is 1000 B. Let's say, yeah, for such a constant B that's given by this expression. Now, a slight change of the X, the data, will give a slight change in the determinant, but then we see the effect of those slight changes into the value of the beta. In here, before beta is 1000 B, let's say B equals 1. So we have beta equals 1000. And when just do a slight change of the data, we get beta equals to 500 of B, which gives us the difference of 500. There is a huge difference in the estimated value of the beta here. So that's why when the multicollinearity exists, this problem here, the unstable condition of this is called the ill condition. the yield condition matrix, and that yield condition gives the consequences of unstable estimated value of beta. What if we just change it? This is also another example of changing it slightly. Then we get that result, and then it's even worse. The difference in the value of the estimated beta. So then this is kind of like the visualization. For example, we have this is x1 and y. The relationship is represented by this line, but let's say there is some multicollinearity between x1 and x2, some other predictor variables in the model, slightly changing the data or additional of a different data point might change, the equation of the line. So previously we have like this, and then slightly changes of the data might change the estimated beta that is represented by this slope in here. Remember before, for example, like we have this is 500B and this is like 1000B, or probably something like this. So then we can see that because slightly changes of the value of the predictor variables might change drastically the value of the beta, when actually beta represents kind of like the partial information that given by this variable in explaining y. So in the case there is some multicollinearity, we not recommend to do the interpretation of beta J in the model. So in conclusion, we may sum up with that statement that multicollinearity is a condition when more than two predictors or more are highly correlated in a linear model. And this might result in an unstable estimated beta parameters.